I saved the lamb data into an Excel file. And so this Excel file is not very interesting, but you can see how I've stored the data. Okay, I've got two columns. One says weight gain and one says group. Okay, and so each row is each lamb, and so this one is the first lamb. It gained 8 pounds or 8 whatever, and it was in group 1. 16 in group 1, 9 in group 1, 9 in group 2, and so on and so forth. Okay, so I'm not putting in summary statistics or anything like that. I'm putting in the raw data here. Okay, so I'm going to import this into R. It's a CSV file. So I have this in here, and I'm going to do import dataset, and I'm going to import my lambs.csv, and it says, does this look right? Yes, it does. Okay, weight gain group, sure. Okay, so I have this, and that looks correct. Okay, and so what I want to do is I want to create an analysis of variance model that models weight gain based on the group. Okay, now I've stored the groups as 1, 2, and 3, so I have to do something which instructs R to treat the group labels as categories. Okay, so I'm going to call them factors. Okay, because otherwise R is going to see this as numbers and numbers. It's going to do try to do a correlation analysis. Correlation is when we have two numeric variables. We'll learn about that next week. But right now I have to tell R, don't take these things 1, 2, and 3 and treat them as numbers. It's not like those in diet 3 received 3 times as much of whatever as those in group 1. So don't treat it that way, but treat them as labels. Okay, so I'm going to say R, and we're going to store something. We're just going to call this the model. Okay, and I'm going to do AOV for analysis of variance. And what I want to do is I want to take lambs $ weight gain as explained by lambs I have to do as dot factor, sorry, as factor lambs $ group. Okay, and so let's take a look at this. All we're doing is we're saying R, run this command AOV for analysis of variance, and what I want you to do is take weight gain. This tilde says explain weight gain by this thing over here, and the thing we're going to use to explain that will be the group, lambs $ group. You guys are okay with this $ notation, right? Okay, and so I say okay, and then that's it. All right, it's done. And so it doesn't look like it did anything, but I can say, okay, well, print out model. If I just type in model, it'll tell me what we see. Okay, and it says, oh, so the sum of squares are 36, and for the residuals, the sum of squares is 210. The degrees of freedom is 2, and the degrees of freedom is 9. It's exactly what we have, right? And we can ask, I can do summary. Give me a summary of the model. Okay, and if I do that, we get the exact table that we produced, right? Degrees of freedom for, it doesn't say between, it says what you used, okay? It says degrees of freedom is 2, the sum of squares is 36, the mean squares is 18, and the F value is 0.771, okay? And so this is the exact same table that we produced by hand, and we said the p-value is greater than 20% because we were just using the reference tables in our book, but R is able to give you an actual p-value here. And so we see this thing actually does a pretty good job. I mean, not a pretty good job, it does the same thing that we just learned how to do by hand, okay? So, you know, when you do analysis or ANOVA methods, you're most likely going to do things on the computer. It's unlikely for you to go through and do these things by hand. But I think there is merit in learning to do it by hand because you kind of get the idea of what each of these things are, you see, oh, here's the sum of squares due to this thing, and we have the residual thing, okay? And you can make an interpretation based on that. Let me, I want to just kind of muck around with something here, okay? So let's go back to our previous slides here. All right, so let's pretend we had some other variable here. Let's look at, let's say these data points were, I don't know, we'll call this group A and group B, okay? So I'm going to add that into our thing. We'll call this the second, and so basically I'm going to assign these to group A or group B based on what we have. So pretty much everything that was over 13 gets assigned to group B, and everything under 13 gets assigned to group A. Okay, so I'm gonna save this and send it back up. And we're gonna do analysis here. Okay, so we can see what will happen. Okay, if we had two groups and this was group A and over here was group B. Okay, we can see what would happen then. Okay, and what do you think will happen? Yeah, well, so okay, so let's yeah, we should see evidence of a difference. Oops, that's the wrong RStudio. Okay, so let me close this out, and I'm going to because I'm doing this in the cloud here. Yeah, our p-value should be quite significant, right? Okay, so let's clear this, and now we're going to open up lambs. We'll do the same thing. Yeah. Row names. No heading. We do have a heading. Okay. Oh, it had to rename it because it doesn't like having things start off with the letters here. All right, so we're gonna say we're gonna make model again. We're gonna do analysis of variance, and we're gonna do lambs dollars assign weight gain as explained by lambs $sign the second variable. Okay. Now I don't have to do as dot factor here because I'm using letters A and B, and R understands, oh, those are letters, those are labels, okay? It's not going to try to treat those as numbers. Okay, so there, it's done there. All right, and so let's take a look at our ANOVA table here, okay? All right, and so here, looking at this, we see, 1 degree of freedom. The sum of squares due to that is huge, 208.33. So the mean squares is this. Our F value is a ridiculously large 55, and so we have a P value that is 2.2 times 10 to the negative 5. Okay, and so when it becomes significant, it starts putting a bunch of stars next to it. Okay, so 3 stars means it's significant beyond 0.001. 2 stars means it's significant beyond 0.01. 1 star means it's between 0.01 and 0.05, and you get a dot or nothing. Okay, and so we see, oh, if something was group A and group B, let's say they were I don't know, different from different when lambs are born, how are they born one at a time, or I don't know? Who knows, right? Nobody here grows up. We're like city folk.
I would assume it's like the same way as horses, right?
Okay, so just like
come out one at a time. It's
yeah.
Not litter.
One, but from time to time it's 2 or 3.
Okay, like humans, huh?
We just got a bunch of baby lambs.
Okay, all right. So okay, so they're coming out one at a time, but So maybe, you know, we have, you know, they're from different farms or something, you know, farm A and farm B. So something is happening that's causing them to gain different amounts of weight or whatever. Okay, so here we have something that's very significant. You know, and we would expect that because looking at the picture, you know, using our own eyes, we can see that it seems like group A is producing values of much lower weight gain than group B, just using our eyes here, okay? But if we looked at it across, you know, the 3 different diets, it doesn't seem significant, okay? And so, anyway, that's what we've got going on, okay? And so you can use R using this very simple command AOV, and you just take your numeric variable, you put it over on this side, you use the little tilde to say I want it explained by this thing, which is should be a categorical variable. If your groups are labeled with numbers, you have to use that function as.factor. So R knows to treat it as groups. Okay? So that's neat, right? Maybe. Okay. Well, and I did want to explain, and I hesitate giving you this lab here, which is another article to read through. But I hesitate because it's not that fascinating of an article. But I'm struggling to find an article that uses simple one-way ANOVA, okay? Because almost all of the articles that use ANOVA use like factorial ANOVA, which I will explain or just kind of briefly go over. But this one uses one-way ANOVA. I guess it's kind of interesting. I mean, I you know, with apologies to Anna Wilkinson and team for saying their work was uninteresting. We're looking at what this article looks at, and you don't have to read this article in the same depth analysis that you did for this last article, okay? Basically, and I'll just tell you what they did. They surveyed a whole bunch of people who are either smokers right now or used to be smokers. And the most important question they asked was, when did you start smoking? Okay, and so they say, oh, I started smoking when I was 15 years old, or I started smoking when I was 22 years old, or whatever. Okay, and so they asked, when did you start smoking? And then they looked at a whole bunch of other aspects about this person, you know, demographic information and things related to their smoking habits, and they're trying to see what is related to a person's age starting smoking. Okay, so our response is the age at which they started smoking, a numeric variable, and they're trying to explain it using things like, I don't know if explain, but they're trying to find relationships between that and things like their gender. Okay, do men and women start smoking at a different age? Or they looked at their ethnicity. Okay, and so they surveyed almost 1,500 people, 1,447 people. Okay, and so and the people that they surveyed, you know, men and women. So there were 807 men, 640 women, and the average age for everybody as when they started smoking was 17.5 years. For men, it was 16.8, and for women, it was 18.3. Is there a significant difference between these two? They did a t-test or ANOVA, and they got a p-value less than 0.001. So yes, gender seems to play a role in when someone starts smoking, okay? Or if it doesn't play a role, at least it's connected to that, okay? They also looked at the ethnicity, okay? And there's 3 categories for ethnicity: non-Hispanic, white, Hispanic, African American. So the study took place in America, and they got these were the different means, and this is the p-value, okay? And so they had to do one-way ANOVA, and the only shortcoming here again is your p-value is 0.001, which means ethnicity seems to be significant, It does not tell us which group, though, is the one with the different mean, okay? Now, looking at the data, it seems like 18.4 is the one that's significantly different from the others. But we can't jump to that conclusion because it could also be the 17.3 because there's, 1,100 people in 17.3, okay? Because, when they surveyed a bunch of people, they surveyed a bunch of non-Hispanic white people. So it's hard to say, okay? It doesn't tell us which one is the one that's different. We just know that it seems ethnicity plays a role. Same with high school attainment, et cetera, et cetera, et cetera, okay? And so for this lab, and please don't hate me for this exercise. It's a simple exercise. I'm just asking you to use one of these summary statistic things and calculate the, try to see if you can get the same p-values using doing ANOVA by hand, okay? And so, for example, I did it for the variable ethnicity, and I said, here's the summary statistics. They provide you with these standard deviations and the means and all of that. So that's actually unique for a lot of articles, is that they provide you all of the details to do the analysis yourself. Okay, and so just plugging in all of this stuff for into the table, I got a p-value between 0.001 and 0.0001 using the F table. Okay, and that aligns with what they report here. Okay, so anyway, that's the article. It's they're just trying to find a connection between different demographic things, and also there's another table going over smoking habits. For example, do you smoke over a pack a day or less than a pack a day? Does that play into when you started smoking? Or does when you started, and of course we don't know what the cause and effect is. It's just, is there a relationship? But anyway, that's that. So I want to talk about, and I'll try to do this in not too much time, just some of the other versions of ANOVA and kind of how they're formulated, okay? So we have, so let me talk about the generalized, what is it called? The F test, the global F test is what it's called. Okay, or the ANOVA model, global F test. In ANOVA model. So for one-way ANOVA, we stated that our null hypothesis is that mu1 is equal to mu2, equal to mu3, equal to mu4, etc. Okay? Now, another way we can do this, this can be rewritten or can be reformulated this way, which is equivalent, but maybe perhaps a bit more flexible for other types of models. Okay? And we can say there is some grand mu, I should say, okay? Quote unquote, grand mean. So this is the mean for everybody in all the different populations. There's some grand mean mu, and each group has a group effect. Okay? So, and the group effects has a group effect tau. Okay? And so in this case, we would say an individual point, an individual value, y is equal to the grand mean mu plus its group effect tau plus some random individual residual. So this is the grand mean. This is the group effect. And this is an individual difference. Okay? And so our null hypothesis can be that tau 1 is equal to tau 2, equal to tau 3, equal to tau 4, and they are all equal to 0, saying that each of the group effects are 0. Does this reformulation kind of make sense? It just feels weird right now. Here, let me try this. Okay, so for example, so one way we can explain different heights. So so if we said we can say the heights of the average height of men in the U.S. is 70, and the average height of women in the U.S. is 64. I'm just making up numbers here, but something like that, okay? And so we can say, you know, if you were to take a man and he is, let's say some man is 69 inches tall, you can say he is 1 inch shorter than the average man in the US, okay? And that would be according to, and this would be more in aligned with our old model of the null hypothesis being mu1 equal to mu2, okay? The alternative forming is to say that the average height of everyone in the United States is 67 inches. This is the average height for all Americans. Okay? And we can say if you are in the group male, if you are in the male group, there's an effect of adding 3 inches to that grand average, okay? And if you are in the group women, that has the effect of subtracting 3 inches, okay? So these two things are essentially saying the same thing, but we're just kind of formulating it a little differently, okay? So let's say we have a man who is 69 inches. Okay, in this formulation, we would say he is in the male group, which puts his group average three inches above the grand average or grand mean, and he individually is 1 inch shorter than his group's average. So I know it feels a little bit more cumbersome this way, but this gives us some more flexibility in dealing with multiple effects. Okay. So, for example, maybe we wanted to get, into further detail about different heights, okay? And we could say, you know, there's, if we looked at different races, you know, the average height for different races is different, right? So we could say being Asian per se might make your group average to be shorter than the national average or something, okay? Or being, I don't know what else I can say about races and things like that. But, you know, statistically speaking, just the Asian demographic has a shorter average. So we could say, so if we were to use this old model, we would have to come up with different, every single different group, right? An average for each group, and we'd need average Caucasian male versus average Caucasian female versus average Asian male versus average Asian female versus average, you know, this ethnicity male and this ethnicity female. With this alternate forming, we can just talk about an effect due to gender and an effect due to race. Okay? And so this allows us for other models here. Okay, so for one-way ANOVA, it looks like this, but we could have randomized blocked ANOVA and maybe two-way factorial ANOVA, and I'll explain these. But I just want to make sure that this alternate formation is kind of okay, talking about group effects. Yes?
It just seems like a lot of words for one value. So are we going to have to describe values that way?
No.
Okay,
It's
okay.
but the model is trying. What you're trying to do with a model is you're trying to explain why the different points have different values. That's what we're essentially what we're doing with ANOVA. We're trying to say, why did this sheep gain so little weight? Well, maybe it was because he was on diet 1, which seemed to suck in terms of weight gain, and this sheep was weird and gained even less than whatever. Okay, we don't know. So you're just trying to explain all of these different things. You know, why was it hot last week? Well, you can say, well, we're in May, and May is generally a warm month. We're in Los Angeles, which is a warm city, or things like that, and there's all sorts of things, but then, you know, why was it a little bit cooler the other day? And then you just have to say, well, weather's crazy, you know? So, but you know, being our location and the season explains part of the weather, and then the other part is unexplainable, okay? But, okay, so we have randomized block ANOVA. Okay, and so here we would say an individual data point comes from the grand mean mu plus its group effect plus a block effect and an individual resistance, okay, individual residual. So this is the fact that it's in a group, this is in a block, and this is a residual. So a block is pretty much a second factor, okay? A block is another factor or variable. But generally, a factor or variable that we suspect has an effect on the response. Okay? But we often are not interested in the effect of the block. Not of the block itself. Okay, so but we don't want it to mess up our model, so we include it in our model in the analysis. Okay, so here's an example. Let's say you're growing plants in a greenhouse. Okay, but for whatever reason, for whatever reason, you didn't design the greenhouse very well, and this part of the greenhouse gets lots of shade and less sun, and this part gets the most sun, and this has some shade and some sun. Okay, so ideally, when you place a greenhouse, you want it to be everything to get lots of sun, but maybe you built it and then somebody decided to build a skyscraper next to your greenhouse or something, so it blocks out the light. I don't know, whatever. But here you want to do an experiment, and you want to know maybe there's different chemical fertilizers, and you want to see what's going to help you grow the biggest tomatoes or something like that. Okay, so you want to know which fertilizer helps grow big tomatoes. Okay, and let's say you have two fertilizers to consider. So you're going to have three groups. You're going to have control, fertilizer A, fertilizer B. Okay. Now, what you do not want to do is, as you're placing these tomato plants in here, okay, let's say you have, what you don't want to do is you don't want to put all of fertilizer A here, all of fertilizer B here, and the control groups over here. Okay? Because if at the end of the study you see that the plants with fertilizer A grew the most and the control group grew the least, you would not know if fertilizer A grew the most because these plants grew the most because they got the most sun, or if because fertilizer A was the most effective. And you don't know if these grew the least because they got the least sun, or the control group was the least effective at producing big tomatoes or something like that. Okay, so this would be a bad design. Okay, so bad design is put all of fertilizer A in the most sun area, etc., etc. Okay, now random design. With random design, you would just randomly assign where A, B, and C go. Okay, so with random, you might end up getting 2 A's over here and 1 B over here, and you might get 2 B's and 1 C, and you might get 2 C's and 1 A, or something like that. Okay, with random. So with random design, you still might have more A's overrepresented here and C's overrepresented over here. Okay? You can still end up with too many of, too many of A in most sun area. Okay, so here we do a random block design. And we would make sure that you have A, B, C over here, A, B, C over here, and A, B, C. You make sure each treatment is properly represented in each block. Each treatment is equally represented in the blocks. Yes.
In the article,
Uh-huh.
they do block, because it says something about blocks of 4 or 6.
Uh,
Like randomization. And I didn't understand it. I sort of Googled it, but I was like,
I don't, honestly, I don't remember. They might have. So we use blocking when, there's something that's out of our control. Like we know sunlight has an effect on how much a plant grows, okay? And we're not so interested in the effect of the sunlight itself, okay? But in order to tell the difference, we have to include that into our analysis. Otherwise, we might see a large variation between the plants in the sun and the little sun and things like that. So by including the sunlight as a block, maybe what we see is that in all 3 groups across the board, in groups with the least sun and groups with the most sun and in the middle amount of sun, maybe fertilizer A grew the most across all 3 groups. That would be pretty compelling evidence that fertilizer A is the most effective, okay? But if you didn't include the blocks in there, you'll just see a wide variety of values for fertilizer A, a wide variety of values for fertilizer B, a wide variety of values for fertilizer C, and you would end up kind of with the effect of the fertilizer being drowned out. It's kind of like in the paired t-test. The individual effect of the treatment is lost. Okay, so that is the randomized block, ANOVA. And then the next one, the other design that I want to talk about is the two-way factorial design. And don't worry, this is the last thing we're going to talk about today. And so with the two-way factorial design, we say each data point y comes from the grand mean plus group effect 1, and what letter do we use here? They use tau, beta, gamma. Okay, so different books use different notation, but we'll have this. We're just throwing a bunch of Greek letters in here. Okay, epsilon is always the residual. Okay, this is always the individual difference, right? So you can say, oh, you are male and you are this ethnicity, and you belong to all of these groups, but you are not the same as everybody else in your thing because of individual differences, right? So we can try to explain, why is this person tall or short? We can say, oh, well, this person is female and is this ethnicity, which in general is shorter than other ethnicities, and et cetera, but she individually herself is short compared to other people in that same group, or something like that, okay? So so here, we still have the grand mean, and we have effect 1, effect 2, and we have an interaction effect. Okay. And the interaction effect allows for kind of this, maybe more so, let's see, it's hard to explain. The two effects. So let's say we wanted to explain height based on gender and race. Okay, so this is probably not the best example, but let's say we said height and we have effects due to gender, and we have effects due to race. Okay, and so gender will be male, female, and race. Yeah, we can, globally, Asians are generally shorter than non-Asians. Okay, so maybe this is a global study, and so maybe being male or female has an effect of doing +3 versus -3, and being Asian or non-Asian maybe globally has an effect of doing maybe +1.5 versus -1.5 as the average or something like that. Okay, we might find that, so if or I guess Asian, non-Asian would be -1.5 versus +1.5, right? Okay. So under this thing, let's say the global grand mean for height is like 66 inches or something like that. This is probably too much of a difference for the Asian versus non-Asian. So according to this, can I change these numbers on us? Sorry. Let me just do plus or minus 0.5, because I think 1.5 is too much for the Asian differential here. Okay? Okay, so globally, let's say the grand mean is 66, okay? So if we were to pick someone who is female and Asian, if we took these numbers, we would expect, what we expect is the average of all female Asians to be 66 minus 3 for being female, minus 0.5 for being Asian, and so we would expect something like an average of 62.5 inches or something, okay? But it might turn out that being female and Asian actually produces an even lower mean, okay, of maybe 62.0 or something, okay? So maybe the average is actually 62.0, okay? So here we have what we call an interaction effect, where this is coming out to be even lower than what we expected. Or the opposite could happen. Maybe it comes out not as low as we expect or something like that. So maybe there's something, not to say that there's some even strange genetic thing happening, but it might turn out that being Asian and female, the average is even lower than what you might expect by just simply adding the effects of male and female, or male and race or something like that. Okay, who knows? So a lot of times that happens, with chemical interactions and things like that. Strange things happen. Okay, so that's all covered in more detail in Chapter 11. If it interests you, most of the homework for this week just comes from the stuff from one-way ANOVA, and a little bit just about the conceptual parts of the randomized block design. Okay? And with that, we'll end a little bit early. Have a good week, you guys.